D-STAR is a collaboration between Cal Poly in San Luis Obispo and Phil Lubin's team down in Santa Barbara. So we work together on a system that we call D-STAR, some phased array laser technology for planetary defense and exploration. What I'd like to do is give a brief introduction to the D-STAR concept, and then talk a little bit about some of the research that we've been doing to develop system parameters, some optical simulations, and some other functions that D-STAR might be capable of. So we'll try to follow this outline. So, I wanted to talk a little bit about the threat, and probably most people in the audience have seen these numbers in other places. I just wanted to review them in the context of what our research is. And so I put a couple of recent events there, the Chelyabinsk impactor at about 570 kilotons, probably about a 90-year event according to the references that are cited there. These are just estimates, and they seem to vary a little bit over time, but those are sort of what we compiled from the literature as they are. The same day that Chelyabinsk impactor hit, February 2013, the 2012 DA-14 was a close approach event. That one, had it impacted, would have been somewhere in the range of 7 megaton explosion. And that's sort of the regime that we're thinking about with D-STAR. Over there on the left is a estimate of the Hiroshima yield at 12.5 kilotons that detonated around 509 meters altitude, according to that particular reference. So I'm trying to think then of D-STAR in the context of this picture and other strategies that might be used to deflect an incoming asteroid that we think will strike the Earth. This is sort of a short list, and I think there's probably a lot of other things out there, but I tried to get a representative sample of what's there, mitigation strategies to try to avoid an impact. So PATE then, induced Yarkovsky effect, or other methods to do that. Focused solar energy, solar sails, gravity tractor, ion beam shepherds, direct motive force, mass drivers, laser fleets or laser implements at the asteroid, kinetic plus or minus armed impactors. In some sense, a short list there of strategies that people have come up with to mitigate an impact. And I was trying to think about, what are the common things that all those approaches have. And, we think of them as stand-on systems. That is, all of the systems that are listed there must be close to or on an asteroid to be effective. They're all sort of dedicated missions to an individual threat that might be coming. And, certainly these are all warranted. All of these things, considering all of these approaches, is warranted in the face of large threats. So I went to the NASA site there and found the most probable known threats, and there are several large ones in there. This 470-meter object, the 2009 FD, has a 0.3% chance of hitting over 5 orbits between 2185 and 2196. So there are a couple of other big ones in there, but to me there seems to be some gray area here for dedicated missions. So if we look at the bottom of the screen there, dedicated missions to smaller objects, a 10 megaton event would certainly warrant some any measures that we could come up with to deflect that threat. But the further you go down the list, there seems to be some gray area for dedicated missions. And in particular, could we launch a dedicated mission every couple of years to something that's in the order of 23 kilotons? I'll go back to this picture and note that the Hiroshima yield was about 12.5 kilotons, and a fairly destructive event. And do we mount a dedicated mission for something that comes around every 3 years, or every 5 years, that yields 23 kilotons? So there seems to be some gray area to me in this particular area of smaller objects. And so, that's in some sense what motivated us to think about this system in terms of trying to do a standoff system that might be used for other things. And that's the D-STAR system concept. And so by now this picture has been circulated quite a bit in several publications. DE star, the way we envision it, would be an orbiting system, solar photovoltaics powering a phased array laser system that would be able to direct energy at a distant target. And so it would be standoff interdiction from a distance, in some sense in Earth orbit or some other position there in space. Phased array technology provides all sorts of different opportunities for other things to do as well. So this would be a multi-purpose asset that could be used at a moment's notice. So in some sense, a very different thought compared to most of the other approaches that have been proposed to mitigate the threat of an asteroid impact. So we call our DE stars by size. 10 to the 0 would be a 1 meter. And D star 0 is a 1 meter array. D star 1 is a 10 meter array, etc. It's completely modular, so you could build such a structure in space and just keep adding to it. So the baseline system architecture we have are these ytterbium-doped fiber amplifiers that lays at 1064 nanometers. Currently, they're approaching about 1 kilowatt per kilogram to get their the power density there. So, and that's rising rapidly, so we could start to consider then some very powerful systems in space. So the baseline architecture that we envision is based on work by Vorontsov et al. Done in 2009, and we tried to extend that technology to a space-based system. So the flow chart, or the block diagram up at the top, shows how we might control the phase of all of those individual emitters. So in the far left there would be a seed laser and a fiber splitter that would feed all of the fiber amplifiers in the middle. Now each of those fiber amplifiers would probably have a different phase at their output just based on temperature distributions and distance to the fiber amplifiers and whatnot. And so there would have to be some sort of phase feedback to keep those the phases at the exit apertures all the same. We envision sort of a beacon reflector out there that's fed by a dedicated laser in the array that then provides a phase reference signal back to the structure. Now that phase reference signal would provide a mechanism for keeping all of the exit aperture phases the same based on the phase controllers. And also, if you modify the reference phase signal at each of the emitters, you can steer the beam from one place to another. So that's the basic architecture that we have, and this is based on work that's been done in the laboratory. So all of this technology is available now. So if we have the technology and we can deploy it, what can it do? So as the previous presentation has also shown, we've done some modeling of the thermal, sort of transient thermal conditions that an asteroid might hold. This would be a 3D simulation. We also have some 2D simulations shown at the right, which are versatile in other ways. And combining those other things, it seems like our results match up quite nicely with the previous presentation. That is, somewhere around 2500 Kelvin, the surface begins to vaporize. And that can, that's somewhere around 10 megawatts per square meter, or a little bit less than that. And that sort of vaporization regime happens fairly quickly at 10 megawatts per square meter. And you can see then that vaporization occurs, somewhere around a second in our simulations. So these included radiation conduction and mass ejection. We did not model the absorption of the incoming laser energy in the ejected plume, but most of the results that we see in the laboratory suggest that about 10% perhaps of the energy in the laser beam are absorbed in the plume as it's exiting the surface of the asteroid. So here's our the beginnings of our laboratory experiment. Now this is being done in air, but we're trying also, almost exactly like the previous presentation, trying to measure the thrust that's generated by those ejection plumes. And so the theoretical curves are there on the left that we've calculated for various mass ejection rates, and for various sigma of the beam coming into the surface. The experiment that's shown there is in air, and we've moved that into a vacuum chamber with a torsion balance on it, so we're trying also to measure those fluxes. The vacuum system also has ports where we can view it with the infrared cameras and match up those thermal simulations that we have with the measurements from the infrared camera as the laser beam is impinging on the surface. So almost exactly like the previous presentation there. So based on those experiments and the theory that we've developed, we've been trying to make some measurements of thrust then, or some predictions of thrust based on the flux that's coming into the target. And so you can see there somewhere between 10 to the 5th and 10 to the 6th watts per square meter, then there's a significant rise in the thrust that comes off of the object. So again, we're trying to use those laboratory experiments to match up with these particular theoretical curves. So if we want to build a system of the block diagram that we said, that we showed previously, what kind of requirements are we going to need for beam formation and steering? So we've been performing also optical simulations on how to control the beam. And so this is just one example of a simulation that we've run, a 6x6 square element with close packed spacing of 10 centimeters. Now this is based on some initial proposals that we're trying to submit to become a secondary payload, on board the asteroid redirect mission, NASA's ARM mission. So maybe something a little bit less than a 1 meter aperture total, then what could we do with that? So here's a 6x6 close packed spacing of 10 centimeters. We could put 36 emitters in there and be somewhere around 40 kilowatts total power. So what would happen then if we were in such a scenario? What kind of power would we might we see? So this particular simulation was done with phase perturbations across the array of about lambda over 10. Now, that's a typical, kind of optical scenario. So, if we can achieve lambda over 10 over the entire array, then we get sufficient flux out in the main lobe of the beam to melt the surface of a crustal rock or anything that might be expected to be inside of an asteroid. So the phase perturbations across the array will lead to some power leakage that you can see there on the right-hand sides. The pictures, those are log axes on the left. So there's some power leakage in the side lobes with various levels of phase perturbation across the array. So, the simulations, we want to try to match the simulations with known theory about how the flux might depend then on the phase error across the array. And so we compared then to Roux theory. There's a couple of curves there in the left-hand graph, Roux theory for 10 apertures and then 5 apertures, and then how our simulations match up with those with that theory, and they seem to match quite well. So you can see then in the bottom right-hand graph, if you can't keep your phase aligned within one wavelength, then there's almost no amplification of the signals at all. So it seems like we need to be in the regime of lambda over 10, and the schemes that we have so far seem to be available or capable of doing that. We'll go back to this one here with that beacon reflector providing a phase reference signal. That's how then we would keep all of those phases in line. Now again, this is based on work by Vorontsov, so we know that this particular method works. So that was optical simulations and the beam formation required for keeping the power high in main lobe and also for steering. Now if we can build such a system, then there's many benefits that could happen here. And so I just want to briefly mention those before we sign off. So we consider this DE star system then an orbital system. Maybe we could initially try to build such a system aboard the ISS, for instance. If we had a 10-meter system or a 2-meter system on board the ISS, what could we do with it? Well, there's the possibility, obviously, of trying to mitigate the threat of an asteroid impact, as shown in the first application there. Well, interestingly, and these are other things that we've been exploring in the laboratory, I'll talk about that in a second, the heated spot on the surface of the asteroid provides a black body source that shines through the emitted cloud. And by observing absorption lines in the emitted plume, it's possible to determine molecular composition of the asteroid. So that's something that we've been working on with some researchers in the UK as well. I'll show you some results there in a second. So that's one possibility beyond mitigating the threat of an asteroid impact that we could potentially accomplish with a DE star in orbit. Another thing would be beamed power. So, for instance, there's a spacecraft there. If you could direct the energy to a reflector on the spacecraft, it's possible to accelerate that craft away from the DE star and toward a planetary objective. So some other things that we have thought about, a defocused beam could be used to illuminate a search area, and so the beam itself is very narrow band. So defocusing the beam and raster scanning the target search area, the return signal would be very easy to see, and you could probably see a lot of objects that are very dim or very small, that are very difficult to detect by other means. Certainly, one of the things that you could do with the DE star if it were in orbit would be to turn it and point it at orbital debris. Now, we've just been studying some requirements for pointing and beam control to try to accomplish a deorbit. So all of those things are there. And so if you build a DE star that's just going to sit up there and wait around for an asteroid to come and hit the Earth, well, that might not be the best use of limited funding. But a DE star that could do many things that are listed here and others that aren't would defray the cost of planetary defense by exploiting funds allocated for other scientific objectives. Here's some results that are shown from Tennyson in the UK for absorption through the plume. So the observing absorption lines through the ejected plume could possibly allow determination of molecular composition. And so we've been modeling along with Dr. Tennyson and others in the UK how that might happen, and it seems like from the initial results that such a detection would be highly likely. It would be quite easy then to see water and, for instance, silicon dioxide or whatever in the asteroids. So another objective then might be illuminating NEOs themselves, and viewing the return signal on Earth would be somewhat easy because the signal is very narrow band. So I'd just like to conclude then with some things that we think are important about this particular concept. Smaller objects create a gray area for dedicated missions. Do we send a dedicated mission to a 10 kiloton, for instance, impact threat? Emerging technologies certainly make this discussion possible. The technology is there, has been demonstrated in the lab, and all of our experiments so far have confirmed the plausibility of this approach. Optical simulations are promising, and if we can build this system, then there are some obvious benefits beyond a dedicated system for planetary defense. Row composition analysis, active illumination and search, orbital debris mitigation, and power beaming, among others. So those represent what we seem to think is a clear synergy between DE-Star and other programmatic needs. So, it's a long-term program and long-term consequences, and please let us know if you're interested in joining this collaboration. Thank you. Some references there for that we're cited in.